Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Now, so far we have met some statistics in Workshop 1 and in Workshop 5, and this is now in Workshop 10. And this is the deferred material. Now, statistics really is kind of broken into two areas. There's the descriptive area, which you did a lot of, okay? And then there's the inferential statistics, which we'll say our ordinary level now leaving cert is this deferred material, okay? Part of it at any rate. And in inferential statistics, we begin to make statements about a population based on a sample of that population, okay? And really there's two ways to go. There is estimation, where you could estimate a point, or there's an interval estimation, and down the other side there's hypothesis testing. So we hope to get through those. We're going to recap on Workshop 5, where you did some work on inferential statistics in the past. So the important prior knowledge will come from there. And back there we analysed right foot lengths as an example of continuous data that would be normally distributed, okay? So the right foot lengths, right, you measure those, so it's continuous data, and it would be normally distributed, okay? And when we look at this diagram here from the sample of 200, we see that it has one mode. It is roughly symmetrical, sort of bell-shaped, so it's tending to be sort of normal, like, at this stage with that number even. And here's what you did, like there's the 200 piece of data that were downloaded from Census at School, and you got the mean to be 24.6 centimetres and the standard deviation to be 4.06, which was approximated to 4 centimetres. And what you looked at is one standard deviation either side of the mean, two standard deviations and three, and we got trying to put percentages on that. And there's your mean, and we count the number in there, and we got 144. Then we moved out to two standard deviations, and we count the number of data points in there, and we got 186. And then we go to three standard deviations, and we got 197. And we put a percentage on those then of 200, and we got the following percent: 72, 93 and 98.5 for that particular sample of 200. Do you understand? Now if we took another sample of 200 down, we may get roughly similar figures, but they may not be exactly the same. Do you understand? Because of sampling variation. Do you understand? Now in that. Now after you concluded all that, then you confirmed what we call the empirical rule for normally distributed data. Okay, now the empirical rule is very important for our ordinary and higher level leaving cert, okay? It is also known as the 68, 95, 99.7 rule, because 68% of normally distributed data is within one standard deviation of the mean, 95% within two, and 99.7 within three standard deviations of the mean, okay? So they need to engage with and be familiar with the empirical rule at ordinary level as well as higher, okay? Is that okay for us now? Now, we'll just move it on a little bit, and if, for instance, we're talking about a population. Now, the population, the mean, the symbol we use for it is mu, and the standard deviation, the symbol is sigma, okay? And these will be important. And they are parameters. And population parameters are usually unknown. We won't know them, maybe. So therefore, we sample and we get a statistic to get an estimate of them. Do you understand where we're going from this? Okay? And again here we see, look, that mu minus 2 standard plus mu plus gives you 95%. And I suppose on our course, the one here is the 95%. And of course, what that normal curve allows us to do is to put numbers or percentages on something so we can quantify. Once the shape was normal, we're in a position of quantifying, you see, which is very important for us. Okay? Now, most important for inferential is 95% of normal data lies within 2 standard deviations of the mean. And that's what's important for us. 95% of normal data lies within 2 standard deviations of the mean. Now, for your higher level, and we just look at these, at our higher level, we may have to go a little bit further. And if we look at the table, okay, and if we look at these Z scores here, if I look at 1.96, I see 0.9750. Okay, now what that actually means is the following, that if I have my normal, and if that's 1.96, from there down, I have 97.5% of the data is from there down. That's the area from there down, okay? So that means up here then, I have 2.5% of the data is left, okay? When you read these as Z tables, and 97.5, so 2.5% is up here. Now, by symmetry, if I go down to the other side and go down minus 1.96, if my center there at 0, so there must be another 2.5 there. And of course 2.5 and 2.5 gives 5. So the green area then in here between these two lines, from there to there, would contain 95% of the data. And it's just a little bit more accurate than the empirical rule, where we say 2 standard deviations for our ordinary leaving set, but our higher would be between 1.96 standard deviations of the mean. Does that make sense? Okay, now okay. Now, your ordinary level student won't have engaged with these as Z scores at all, so you wouldn't be mentioning those terms. It's your higher level student. Okay, now, let's take a question you work with. You wanted to work out which mobile phone company is the most popular among Irish second level students. You used a sample of 100 students and found that Meteor topped the survey with 42%. What percentage of all second level students in the country use Meteor? Okay, so what we're actually saying is here, can we use the sample to talk about the population? You know, so can we use the sample of 100 there, and the n there, the sample size, the letter we use is n. N is equal to 100, and we get then the 42% is a statistic, and you get a statistic from a sample. A parameter is what refers to the population. You get a statistic from this, okay? Now, and the 42% is a statistic. So for example, could I make the statement, well, 42% of all second level students use Meteor? Like, could I make a statement as bold as that, or as deterministic as that? And I have to say no, right? Now, I can't, because If I took another sample of size 100, I may get a different proportion, like a different percentage. Do you understand? And we will look at a moment in a thing called sample variation. And that's you met in workshop 5 as well, where you all sampled 30 from the grouping, and you ended up with different dot plots, like different groups, okay? And sampling variation. Now, no one sample will bring down every characteristic of the population, would it? But the whole idea is to get as many of them as possible. And of course, that means then what type of sampling will we do? We have to use a thing called a random sample. And in a random sample, everybody has to have an equal chance of being selected. If you have any sort of bias in your sampling, well then the data that you're using is not reliable, you see. Okay, it's only reliable if it's a random sample. Now, we will just look at page 3 there, and we look at some of the questions in your workbook there. So if you just turn to page 3, and the data for the line plot is from 2 classes in a school. The sample size is n equal to 59. Describe the data in as many ways as you can using numerical and shape descriptions. Words, fractions, decimals and percentages can be used in your description. Now, you must describe the data, numerical and shape description. So first of all, let's look at the shape there. So what would we say about that? It has one mode, yes, yeah. Could we say it's symmetrical? No. Roughly, yes, yeah. Now, because just a point there on that, if we said it was symmetrical, you see, I should then, not having seen it, should be able to draw it. And of course, I could draw a symmetrical one and say, look, is that what you described? Because that's symmetrical. No. So remember, like, to tell the students to describe what they see, maybe not what they like to see, like they're, what you see. So as you said, roughly symmetrical. A lot of the data are clumped around 4, 5 and 6. Couldn't we say that, like, if you do a bit of 22 of the 59 are in 5 actually, so you can put a percentage on that. And if you add 4, 5 and 6, you get 47 of the 59 are there, and you can put a percentage there. So, you can easily describe that. Is that okay for us? Now, one person, number 2, was absent on the day of the survey. Someone said they would give you €100 if you could guess the number of people that's in that student's household. What number would you guess? Anybody, would we try a number? 5, I suppose? Yes, yeah. We go with 5. Why would we go with 5? We give a reason. Because it's the most popular number, isn't it? Yes, yeah. Okay. Now, describe your chance with this number. Well, I mean, you could go back to my one there. Well, I'd have 22 out of 59, whatever percentage that would be, like, in that. How would you increase your chances of winning? Maybe go for 4 and 5 or 4, 5 and 6, wouldn't it? Just extend it a little bit. Now, and of course, keep going into a wider interval will help you. Now, what about number 8 I'm interested in? Is it possible that a student who was absent could have 8 people in their household? Is it possible? Yes, possible. Yes, yeah, that's all we want. It is. Of course it's possible. Now, number 9, is it probable that a student who could have 8 people in their household? No, not very likely. Okay? Not very likely. So it's possible, but not very probable. Yeah. Okay? Now, you see, is it possible to have somebody with 9? Of course. But on the evidence of the data, it's not very probable, you see. We can only work on the evidence we have. It's not very probable. Is that okay? Mm-hmm. Now, that gives us an idea there of developing ideas there and words. So for your ordinary level, they need to be able to put words in. But it's very important that when they're describing something, you describe what you see. And it has some characteristic that makes it stand out, like one mode. you know, don't ever be over deterministic, like, you know, roughly symmetrical, because they will never be fully those things, okay? Now, moving on then from that. So, important with inferential statistics, indeterminate language when inferring from a sample to a population. So, around tends to approximately. So, I could state that around or approximately 42% of students in Ireland use Meteor. And that would be very good percentage for my total population. I'm not saying 42%, I'm saying around 42%. How am I allowed to say that? Because that's the one sample I have, so that's the only thing I can go on. So I can say in and around 42% or approximately 42% use Meteor. Okay? Now, new terminology. Here's our question again, like 42%. So what percentage of all second level students in the country use Meteor? It's categorical data, let's, okay? Because the answer is, yes, I use it, no, I don't. Do you understand? Okay? Categorical data, yes, I use Meteor, no, I don't. Now, how can I represent categorical data with a number? And of course, the answer is by using a percentage or a proportion. Okay, and that's where we have a sample proportion. 42% use Meteor, so 58% don't. And of course, once I know the percentage that use it, I automatically have the percentage that don't, because it's, you know, taken from 100%. Now, it might be useful as well to transfer that to decimals, because sometimes they're working on decimals, okay? So now for my categorical data, and that's what's on for your ordinary level student, it's sample proportions, okay, and it's categorical data. So you'll be showing that things like a bar chart or a pie chart, like, you know, if you were drawing it, okay? Now, a symbol, and some of these now are for us as teachers, and others we may give to the students, okay? Now, the population proportion, you see, so when I'm dealing with proportions here, the population proportion, the letter we use is P, okay? And the sample proportion, the letter we use is P hat. It's just a little symbol over there, P hat. That's your sample proportion. Okay? And so our P hat here is our sample. So it identifies the population one from the sample. Like, for instance, in the means, the population mean is mu, the sample mean is x bar, you know, that symbol. So we'll meet that in means later on. I'll talk about those, okay? Now, so our sample proportion there, P hat, is equal to 42%. In this particular case for us, is equal to 42%, but I cannot say that P is 42%. But a good estimate for P would be 42%, wouldn't it? It's my only estimate that I could use. So now I have an estimate now. So I want to see how confident am I in that estimate, like, you know. So I can say around 42% of students in Ireland use Meteor. So how confident are you in your statistic? I am reasonably confident that the percentage of students using Meteor is around 42%. So I'm reasonably confident that it's around that, okay? I did my survey, my sample. I did a random sample, so I'm reasonably confident that I got a good representation of the students in my sample, okay? Now, but you see, that's the words. It's like the possible. We need to quantify now. So when we take a sample, we need to infer to the full population. Okay, we need to infer to the full population. So I could say I am reasonably confident, I am fairly confident that around 42% use Meteor. Okay, I am fairly confident, I'm reasonably confident. Now, leaving cert, ordinary level and higher level, we need to quantify that. So we need to use some sort of an interval balanced with confidence in that interval, okay? We need to, in other words, put a number on it. So we're going from the possible to the probable. Does that make sense? Is that okay for us now? Yeah? Okay, now, so I'm going to use an interval balanced with confidence in that interval. I am 100% confident that between 0 and 100% use meteor. Yeah, my confidence is sky high. Yep. But of course, my limit is, that's the extent of the limit, isn't it? So I've covered everything, so I have to be fully confident. Now, what will happen if I want to narrow my limit interval here? My confidence must come back down a bit. So I just made this one up. I am 50% confident that between 40% and 45% use meteor. I am 50% confident. Now my confidence has dropped, but my interval has narrowed. Do you understand? So we're going to be trying to get a balance between the two. Is that okay? Now, we have a nice question here from Census at School in Phase 11. Where did you keep your mobile phone last night when you were asleep? And they were the 4 things. Under your pillow, in your bedroom, number 2, in another room, another, please say. So we're going to have a simulation activity here, a sort of a hands-on one that we're going to deal with. So in the bag here, I have 200 discs to represent all 200 students in a school. So let's say that's my population now. Now, why 200? Well, if we're going to put these together, if a teacher is going to, they're unlikely to put 1,000 of them together. So you might get somebody to put 200, yep? And what we're going to do is, the yellow ones in here represent the students who slept with their mobile phone under their pillow, okay? We take a sample of 25 discs from the bag and see what proportion or percentage are yellow, okay? Now, we want just to show students how that we could physically sample. We'll also use IT then to generate other samples, do you understand? But just how we could physically sample. So, in reality, I suppose we'd say, well, if I had 200 in the school, it would be a lot easier for me to ask every one of them, wouldn't it? But we're trying to just model the situation here. So imagine our population was 20,000. And then I had to sample from that, you see. Do you understand? So we're just, and I'm going to break a rule here. Generally, your sample size should be 10% or less of the population. It's called the 10% rule. And of course, if my population is 200 and I'm taking out 25, I now have broken that rule. Okay? Now, why? Well, 25 is a nice number because 425 is 100, so I get nice percentages. And you make it nice and easy. So once you explain to them, this is a modeling exercise. This is what I want to get from this. Another problem then is I take out this yellow fella now, and I look at it and I say, that's yellow. Now, if I put that aside, do I sample with replacement? Do I put it back in or without? Okay. Now, if we're sampling from an infinite population, you say, you can sample without replacement because like 1 over. Do you understand? Now, it is legitimate for us to sample without replacement because we're going through the process only. We're only trying to model. If, for instance, it was 3.43 million and I ask you the question, you can't be asked the question again because, so I'll have to go to the next person. Do you understand? So it should be, you could see there that there wouldn't be a replacement in if we're asking the question. Now, if I put this back in anyway, how am I to know that this was the yellow that came out? Unless I go yellow 1, yellow 2. And, there's nowhere we're going to do that. Now, of course, if you have an issue with that, you could put 2 bags of those together, get 400 and take 30 out of it and you were fine. But it's really, I think it's just a process, okay? Is that? Now, so what we'll do then, we'll just do one of them at random. And so will I give it to you lads now? I'll show you, and I'll set up a thing here. It's just on the board. So we're setting up, so we have yellow and not yellow. Okay, and I'll just do a sort of a tally, and then I can get my percentages after. So maybe if one of you now just, if you put your hand in, and if it take out one, and if it's yellow, say yellow, and then you can just at random. Okay, so you can do it, Celine, if you want to, yeah, and just tell me, and you can put it aside, not yellow. Yeah.
You don't have your blindfold on, no?
It doesn't matter, like, yeah.
No. 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 No.
Yeah.
No.
Yeah. We might get a good result here yet. No.
No.
Yeah, that's 10.
No. Yes. No. 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 Yes. Yes. No.
That's 15.
No. Yes.
How many do we know? 5, 10, 15, 20. You need 5 more. Yes, yeah, yeah.
Yes. Yes. No. Yes.
One more, so, yeah.
Yes.
Yeah. Okay, now, so we see there, and you can toss the other fellas back in. Okay, now, so we're just doing a little bit on the tallying, and we got 5 and 3, 8 out of 25, which is 32%, isn't it? Okay, so we got our 32%. Now, on other days, we got these kind of percentages. We got 20%, we got 24%, we got 28, we got 36, we got a 40, we got a 48. Okay? And what is that showing us? Like really, some days we get 3 groups to do it, like, and we all get hopefully different groups. There's sampling variability, like, you know? Is that okay? Okay, so no, it's just to show them how to physically sample, and this is how it's done. Are we happy enough with that? Now let's look at, yeah, my one actually, that, and I just changed this one last night. I used different ones this time. I didn't think it was going to come to, it came to 32. You know, it. We were getting 36, and I had that one up, and I said, I'm going to keep changing them now. Will I get a different one? Like, you know, I'll have to go down to 20% now, maybe for tomorrow. So, like, there's your one, and there's my one, the same. So we have our proportion, and we're now going to infer to the population of 200 students. So just keep in mind now again, my sample size is 25. Celine did a random sample. In other words, each disc in the bag had an equal chance of coming out, okay? And we're just ignoring the little bit there with the not replacing and all this, okay, in the finite sample, okay? We can ignore that, and the 10% rule. Okay, now, so what we're looking for, can we say that 32% of these 200 students sleep with their phone under their pillow? So can we make that bold statement, categorically state that, and why? Well, the reason we can't is because, look, we could get with different samples, different proportions, and this is sample variation. So we got to keep that in mind, sample variation. So our language now will be not over deterministic. Is that okay? Now, moving on. So could you get a sample of 4%? Well, I suppose it's possible, isn't it? But unlikely. Now, do you see now, we're trying to get the students to go from the possible to the probable, like what's the probability would be small enough, like, you know, and we'll see that. In the old days, they picked the Irish rugby team. The final trial was the probables versus the possibles, you know. And if you were on the probables team, you were more than likely on the team, like, for the thing, okay? So how likely? Not very likely. Was it possible to get 40%? Well, it was, because we got it there on a particular day, like, it's possible. How likely is this? That'd be more probable, wouldn't it? And more likely than 4, certainly, you think. Now, where would you think most of these fellas will lie? This is where we're going, you say. So where will all the sample proportions, or most of them, lie? The middle, yes. And the middle will be where the true proportion is. Okay. And there we see it, of course. And once it's normal, I can apply the empirical rule. And the empirical rule, well, it tells me 3 things, really. It tells me that 68% is within 1 standard, 95% within 2 standard deviations, and 99.7 within 3. But for us and our course, the most important one is the 95%. And we know that 95% of the sample proportions will lie of the true population proportion. Now, as it happens in this case, from the 7,150 students that took the survey in census at school, 30% of them said they slept with a mobile phone under their pillow. So we actually know the true proportion. So your sample, Celine, was a very good estimate, wasn't it, for that? Does that make sense now to us? Okay, now, if I move out 95%, roughly 20% on either side of it, so between 10% and 50%, I could say that roughly 95% of the sample proportions lie in that interval between 10% and 50%. So now I'm creating, first of all, I have an estimate for the true proportion, roughly around 32%, I could say, like, you know. Now I'm getting an interval. So the results lie around the true population. Look, most of them there, look, or a lot of them lie in and around the 30%. So approximately 95% of the sample are between 10% and 50%. Approximately 95. Therefore, I can say I am 95% confident that the true proportion lies between 10% and 50%. Okay? And that's the confidence level I need to be at for my ordinary and higher, 95%. That's the confidence level. When you go to third level, you have a 90% and a 99%, but we don't have to deal with those. Does that make sense now? Okay, now, in reality though, I won't have the benefit of generating a couple of thousands of those. I'll have 1 sample, not 300. I won't know the true population proportion. Well, that's what I'm looking for, so I won't know that. So we will create an interval of 2 standard deviations around the proportion we have from our 1 sample as our best estimate. So I'm going to get an interval now around my sample proportion. And if we look there then at the sample proportion we had was 28%. So we're going to go around that, you know, up and down and create an interval. Okay? Now, this is where there's a bit of a leap, let's say. Okay? I am 95% confident that the true, like between that and there, so the 32%, look, that the true one is in there. Now, this is where this margin of error comes in. One over root n, and that's known as the margin of error, okay? And it relates to n is the sample size, okay? So 95% using the margin of error around the sample proportion. Now, the blue dots here. Now, these are all the different samples we took, look, 20 of them. Now, what do we notice? There's one more, okay? If I took lots of random samples of this size and created confidence at 95 around the sample proportions, 95 would capture the true population proportion. Now I know the true one here, and I went you know, between 50 and 10%. And what do I notice about the blue dots? Look, it's capturing nearly every one of them. Yeah, and it's missing one. Now this is just to show you, 19 of the 20 are captured, so we're capturing 95% of them, and there's one that will always be not captured. Do you understand? Just to, you know. Now, and it's a bit like distances. How far is it from here to Cork? Well, it's the same distance as it is from Cork to here. So like if the blue dot is captured by the true proportion, that interval, well then the true proportion is captured by the interval around the blue dot, isn't it? And this fella here, look, was missed by that, so its interval will miss the one. Now, the thing about this is, lads, that might be my sample. I won't know. Maybe that was my sample. So that's why I will be 95% confident that I won't be 100%. Does that make sense? Now, so why does the sample size feature in the formula 1 over root n for building a confidence interval? What do you think happens the margin of error as the sample size increases? Now, we could certainly put our ordinary level students working with this. And that's really a question for intuitive understanding. Get them to think about it. Now, if you increase the sample size, what do they think happens this margin of error? Like they're looking at this margin of error here, 1 over root n. Now, I mean, if that was 100, or if that was 25, like say, it would be 1 over the square root of 25, a fifth, that would be 20%. Now, if that was 100, you square root of 100 is 10, then you have 1 over 10. The overall is getting smaller, isn't it? Yeah, so now, so definitely the sample size has an influence on our limits here, hasn't it? Okay, so we'll just say there is a direct relationship between sample size and the margin of error around your statistic. As we increase the sample size, what happens to the margin of error? It gets smaller. Okay, now let's look at different. Now remember, different sample sizes. Remember, our confidence is always, now it's inbuilt, is 95%, okay? Our margin of error. So sample size of 25, 20%. Sample size of 100, 10%. What do we notice? A nice question they could ask students is, that's why they need to engage with this, is if you double the sample size, do you have the margin of error? No. In fact, you have to go 4 times the sample size to have the margin of error. And look as we go down through it, lads, look. 400 is 5%, look. 1600 to get to 2.5%. Now, so if our example was 1008 was roughly 3.1%. So roughly 1111 will give you a 3% of a margin of error. And that's why in all those opinion polls, they say roughly 1,000 people were interviewed at different points around the country, you understand? And it's acceptable at 3%. Now, it's manageable as well, and it's cost effective. If I wanted to get a 1% margin of error, I would actually have to poll 10,000 people. And of course, that might be too expensive. Do you understand? So you tend to not go above this, and sometimes you're down. It might be acceptable to have a 5% maybe, or even a 10% margin of error. Okay? Is that okay now for us? Now, so moving on from that, the real life question then, what percentage of all post-primary students keep their phone under their pillow using different sample sizes? Let's say you took a random sample of size 25 from the population of all post-primary students in Ireland, and 7 of the 25 keep their mobile phone under their pillow. Now, let's work out the sample proportion is 28%, the margin of error is 20%, so we go 28% plus 20 and minus 20. Now, we can say that we are 95% confident that between 8 and 48% of post-primary students keep their phone under their pillow. Now, it's still a very wide limit, isn't it? Now, my confidence will be still at 95%. So how can I narrow the limit a little bit? By taking a larger sample size. And if I go up now, look, and do the same thing for 100, look, and I'm going from 18 to 38, I've narrowed it much. Okay? If I wanted to go a little bit further to 1111, these are just the same maths now again, look. And I'm now 95% confident that between 25 and 31 keep their phone under their pillow. Okay, so the sample size has an input into the interval limits. Okay, is that okay? Now, for your higher level, you might have to be a little bit more accurate. So rather than the 1 over root n, we might have to build limits around the 1.96 minus 1.96. So that's the margin of error there, confidence limits there and that. So that's your ordinary level. So basically the one I had written on the board there, look, 1.96 times the square root of p over n, that one, plus or minus that. And of course, if you won't know p, so you'll be subbing in p hat as your best estimate. And that would be just, it's more precise. And I'll show you now. Remember the first one we did with the sample size of 25, we got from 8 to 48. Let's see what happens when we just sub it into this fella, look. Look. What do you think? It went from 10.4 to 45.6 rather than from 8 to 48. It's a little bit more precise. The reason being that the 1 over root n is the maximum radius that it can be. So this fella has to be a little bit, okay? Your higher level student would have to engage in that kind of activity for their questions. And you're still the same, look, 95% confident between 10.4 and 45.6 keep their phone. Now, you get more information there on in the NCCA website under frequently asked questions. Now, I have a copy of some of their stuff here that I'll give you. There's 4 pages there, very good summary that you can read, and it actually explains the kind of answers they require as well. It's good for your, okay. Back in workshop 5, we did it for higher. Now it's also on for ordinary level. Therefore, we'll revisit the hypothesis testing from the workshop 5. There's no point in that stuff was already done, so we'll just go back on that. And this is what has happened now for your present 5th years. This portion has been sitting over here for the last few years under the higher section and the learning outcomes. In other words, recognize the concept of a hypothesis test, calculate the margin of error for a population proportion, and conduct a hypothesis test on a population proportion using the margin of error. So now we've all the groundwork done. It's only a simple step up now to finish, and we have our ordinary level material finished. Is that okay for us? Testing claims about a population. The null hypothesis, denoted by H0, is always a statement about the population. Right, so you make a statement about the population. That's what your null hypothesis. Your ordinary level student has to engage with the concept. So we would sort of tell them what a null hypothesis is. You might mention to them that there's such a thing as an alternative hypothesis, like your higher level would have to engage with that. And the other point about the null hypothesis, statement is true until proven otherwise. It is true until proven otherwise, okay? A bit like the court case, you start with the assumption of innocence, okay? And we'll link to that in a moment. Now the claim. A drug company claims that the new drug relieves migraine 70% of the time. Okay? So we're going to test their claim. So how do we do? Well, a newspaper investigate by getting migraine sufferers to try the new drug. They get 100 results that say it relieves migraine 62% of the time. Okay? So what we've got to do now is, can we believe the company's claim? okay? So we're going to create our margin of error like 1 over root 100 is 10%. So we'll build that around the 62, okay? And the 70% falls within the limits, so therefore we fail to reject. Now, it's important here, they don't use the word accept. So far they've been, you either reject or you fail to reject. In business, I think they use the word accept the thing, but statisticians fail to reject or they reject. So they fail to reject the company's claim. Now, we can stretch it a bit more at the 5% level of significance, because you know that 5% out there from the 95. Okay, we fail to reject the company's claim. Does that make sense now for us? Now, so we fail to reject. Now, we'll take another one. A teacher, she claimed, going down the corridor, she was looking at the students and she said, they're getting taller, right? You know? So she said 30% of second level students in Ireland are 180 centimetres tall. That's her claim. Okay? So now, how are we going to test the claim? Of a sample of 200 students in a census at school, 34 are 180 centimetres or taller. Is this sufficient evidence to reject the teacher's claim at the 5% level of significance? Is there enough evidence there to reject her claim? Okay, so let's get our margin of error now and build it around our 34 over 180. So the margin of error is 7%. The proportion is 17%, 34 over 200. Now we add and subtract 7 to that, between 10 and 24%. They're our limits, yeah? Does the 30% fall within those? If it does, we'll be failing to reject, but if it's outside it, we'll reject her claim. Okay? And the 30% is outside, so we'll reject the teacher's claim that now the claim is that 30% of second level students in Ireland are 180 centimetres or taller at the 5% level of significance, and we'll have to get them into the habit of writing out the answer. Does that make sense now for us? So we try to start by getting a sort of a point estimate. Then we created an interval into which the true proportion would be, and now we've moved and checking a hypothesis based on that. Is that okay? Now, under workshop 5, there are some nice questions done as well that you could just, if you didn't have the booklet, you can actually get them back up on the, if you go into the modular courses again. Okay. Now, they like questions where you're testing a claim and there's an action required afterwards. You know, you have to take some action. You know, so Go Fast Airlines provides internal flights in Ireland, short-haul flights to Europe and long-haul flights to America and Asia. Each month the company carries out a survey among 1,000 passengers. The company repeatedly advertises that 70% of their customers are satisfied with the overall service. So the 70% there now is the claim, that's the company saying, that's your null hypothesis. That makes sense? Now, 640 of the 1,000 in that particular month said they were satisfied. So that's now where you're looking for the evidence. Do you understand? Now, if we link it now to the courtroom analogy. At the start of a trial, we assume the defendant is innocent. Then we present the evidence. The verdict is guilty or not guilty. You know, if you think about it, you're actually never proven innocent. You're either guilty or not guilty based on the evidence, right? And then finally, there's an action. Well, the judge decides on the action, like, you know, if you're guilty or not guilty, okay? So we're looking for writing the thing in a real world context, and then a real world action is sometimes required, okay? Now, so the null hypothesis is the proportion of passengers who are satisfied with the service is 70%, or if you want to write down P is equal to 70% or P is 0.7. Okay? Or H naught for a higher level student would engage with something like that. They would say H naught P is equal to 0.7. Okay? Now, if you wanted to give them an idea of an alternative, it is quite straightforward. The proportion of passengers who are satisfied is not 70%. So you're either satisfied 70 or you're not. So the alternative, now they tend to use H1 in the SEC, so we'll say P is not equal to 0.7. And there's your higher level there now as well. Okay? Now, in the third level, they know they use A, I think they're an alternative, and that's it. But so far from what we've seen from the SEC has been a 1, okay? Now, so, you know, it would be good maybe to show the ordinary level that there is an alternative. Now, the evidence then. Well, the sample proportion, or p hat, is 640 over 1,000, which is 64%. The margin of error is 3.2%, rounded up. Okay? 0.0316, 0.032, 3.2%. Now, what we do then is we'll add 3.2 to 64 to give you 67.2%, and we'll take it from 64 to give you 60.8. And we've created our limit here now. Look. So there's our limit. Okay? Now we test our claim, which is the 0.7 or the 70%, and it doesn't fall within those limits. Okay? So what we say, the conclusion, the 70% is outside the range of our confidence interval. There is sufficient evidence to reject the claim. Okay? That the percentage of passengers who are happy with the service is 70% at the 5% level of significance. So there's enough evidence there at the 5% level of significance. Now, the actions then. Well, you could change the advertisement from 70%. Okay? Now, you could meet with staff to come up with suggestions about how to improve the level of satisfaction. Now, you could also look at it, maybe that month, maybe it was just a particular, like that month that you had a bit of, that was a bit low, like, you know, that you might have a better on another month. Do a further survey, maybe. Find out more detail why the level of satisfaction has changed. Okay? So, you know, possible type actions, and they like that thing where there's a real world action like as a result of it. Now, is that okay then? Does it make sense? Yeah. Now, so that takes us through. Now, for higher level, look, well, I have this gone through there, so there's your alternative, and then, now we'd have to work out the confidence limits there, you know, the 1.96 into P1 minus P over N, so that's 3%. So 61 to 67, the 70 is outside it, so we reject the company's claim, you know, and then we have the rest of the sentences, how to finish them. Okay? So it's just a bit more precise in that. But of course, if you're rejecting it at 1 over root n, you have to be rejecting it at this. Now, we'll just push it on a bit. We have about 20 minutes, so I'll push on and do as much of this as I can. It's the maths actually are not difficult, but we might do a little bit of sampling, and we'll be basically looking at sort of from pages 4 up there. Here are some distributions. These are population distributions there now. So you can have ones that are skewed, that are approximately symmetrical, unimodal type of thing, and you can have uniform ones like this. You know, birthdays, rolling a die. If you roll it often enough, and it's a standard unbiased die, like, you know, in the end, they'll all sort of come out to be the same. You know, it's whether it's 6-sided or a 20-sided or whatever. Now, we're going to look at this. A sample of size n was taken from the weights of school bags of post-primary students. The mean of the sample is 4.5 and the standard deviation is 2.5. Now, this is the kind of question we're going to get, but we're going to develop the theory around this before we answer it. Okay? So we'll be asked to write a statement about the population mean, stating the level of confidence you're using. Okay? Now, on page 9, we have a summary of findings page there. You know, so you'll be filling some material into that. Now, but before you do, we're going to look at, I want you to look at page 4 and questions 1, 2, and 3 there for a moment. Questions 1, 2, and 3. Now, look at my statement here. One mode, symmetric and bell-shaped. We might question symmetric, mightn't we? So what should I put in there? Like, this is just to get us a bit of a discussion going. Roughly symmetric, I'd say, wouldn't we? We wouldn't be over-deterministic there. So I'd say it has one mode, roughly symmetric, and it is approximately bell-shaped, like, you know, or approaching bell-shaped. Now, what about the center of the data? Where do you think would it be located? Well, when I look at mine here, it's located in and around 5, isn't it? Yeah, in and around 5. So we'll say around 5. Now, the spread of the data. So you could look at the range there if you wished, and it kind of runs from 0.1 to about 9.9. Like, you know, doesn't it? It kind of, you know, it just starts a little bit after 0 there and stops just short of 10. So all the data is between roughly 0.1 and 9.9. Now, if you so wished, you could look at the interquartile range and have a look at the middle there, like, and see that where the middle 50% is, if you wished as well. You could talk about that. Does that make sense now for us? Now, center, shape and spread. Now, before you take some samples from the district, you must make 2 predictions. And prediction is very important, lads, that we make a prediction. If you took a sample of size 30 and found the mean of the sample, describe the chances of getting a mean of between 1 and 2. Now, look at the diagram there, and you took 30 from the population there, 30 pieces of data. What would your chances of getting a mean of between 1 and 2? That would mean now you'd have to get a mean of 1 point something. So what kind of numbers would you need to get? You couldn't have many numbers now up at 9.5 and things, you couldn't. So would your chances be very good or not very likely? Not very likely. They'd be small enough, wouldn't they? Yeah, they'd be small. You know, small chance or unlikely. Is it possible? Yes, but not very probable. Possible, but not very probable there for that one. Now, if you took a sample of size 30 and found the mean of the sample, what would you expect to get now? Which number would you expect would be a good, would you get? 5-ish, yes, in around 5 again. I'd expect to get 5, around 5. Does that make sense now for us, yeah? Now, we'll just build it up then. How many different samples of size 30 can be taken from a population of size 200? Now, remember, we have 200 and we're selecting 30 at a time. So therefore, we're on to our 200 C30. Now, when you put that into a calculator, it turns out to be a pretty big number. Look, that's what it is. In fact, it is 4 by 10 to the 35 approximately. 4 by 10 to the 35. That is the number of samples that you could possibly take. Yeah, isn't it? Yeah. And I think myself, you know, when they begin to see it, we used to play basketball, like, and you had 12 on the panel and the starting 5. And when you ask them how many different starting 5s, 12C5, and when they see the number that comes out, like, they're amazed. Like that you know, that they could have so many different groups of 5, like, you know. And even if you take small numbers, they're kind of amazed, aren't they, like, in a way, at that. Okay, now, that's that bit there. Now, what I want you to do is to look at questions 5, 6, and 7. How you can set up your calculator so that we're all ready to go at the same time. Okay, now, so we'll go AC there. Now, if you go mode 2, mode 2, 1, mode 2, 1, and you create a table like this, mode 2, 1. Now, all you have to do is, somebody does the sample, calls out the number, somebody writes it down, and somebody puts it into the calculator, and you equals it, and then you do the second one, the third one, and do 30 of those. Is that okay? When you get your 30 in, you just go AC, and then you go shift 1, 4, and then you have X bar, you say, X bar is your 2 equal to, so I got 5.95, say for me. Now I only put in a few of them. I can go AC then again, and I go shift 1, 4, 4 this time now. 1, 4, 4, and I'll explain that to you, and that's 2.3. Okay? So AC, shift 1, 4. Now, there are 2 standard deviations here. Okay? So you have sigma x and Sx. The sigma x would refer to the population standard deviation, the Sx to the sample. And since you're dealing with a sample, you'll be taking 4. The Sx is from the sample, the sigma would be the population. We'll move on. So now you have 20 samples done, everybody. Okay. We actually have the stuff there. Look, mode 2, 1, and then press equals, shift 1, 4, 2, and 1, 4, 4. Like, you know, so we'll give you that as well as you get into the stats mode. Okay? Now, correct to 1 decimal place. Yes, now, what I want to look at is, if we fast forward it for a moment to questions 7, 8 and 9 over on, and we have about 10 minutes maybe to get to this, and I'll get as much of it as I can done. Okay, you did 5 and you got 5 point something, I presume, or 4 point something, and you got 2 point something for your other one there. So that's grand. Yeah. Now, go to number 7, and it says find correct to 1 decimal place the mean of the second last column. So now we won't have time to do it, but what you'd actually do, look, is take this column here and put all those in and get the mean. You know, the second last column. So the numbers like 4.9, 4.8, 4.6, 4.7, 4.9, 5.5, 4.7, 4.9. Do you know those ones? Now, if I just skip through, supposing as if we had it done, what do you think would it be? Wouldn't it be about 4 point something or 5? Yeah? Because they're all in and around that, isn't it? Like when you look at them. And what do you think would you call that mean? What name would you give that? The mean of the means. Yes, it's the mean. Yeah, it's the mean of the sample means, if you want to call that the mean of the sample means. Now, compare this one to the population one, mu, which is 5.1. Your answer there is going to be very close to 5.1, isn't it? You know, and it's close to 5.1 because you're doing up ones like 4.9, 4.8, 4.6, 4.7, and so forth. Now, write down the range of values in the second last column. Well, they go from about 4.4 to 5.8. Looking at it there, so the range is about 1.4. Compare, what do you call this range? That's the range of the sample means. When you compare this range to the range of the population distribution, which is 9.8 kg, what do you think happens? It's much narrower, isn't it? Yeah. In this particular case, because you have so few of a sample, you've only 20 of a sample. If you had more, it would be, if you had all of them, it would be the same. Okay, now, just a point on those. If you go to the SEC homepage, you can pick up the sample papers there for 2014. And if you scroll down there, there's actually a report on trialling from the original schools. And it gives you the questions that were on the trial, which were basically the first sample paper almost, and sample answers. And, you know, what they expected the answer. And it's done for all levels there, okay? And you can download that. And one of the things there was when they spoke about, look, the shape of the distribution there, it was roughly symmetrical, bell-shaped, not skewed, mound-shaped. Location of data, look, average around 170 centimetres, mostly around the low 170s and so on. And just on the spread or the dispersion, most are within 10 centimetres of the average, and the interquartile range is about 10 centimetres. So they use the interquartile range a bit more so than the range, like, you know, so it's important to keep that in mind. Remember the interquartile range, no matter what the distribution looks like, the middle 50% is going to be in there, okay? You know, whether it's skewed or not, the middle 50% is going to be in there. So, number 9 then, calculate the one decimal place, the standard deviation of the second last column. What do we call this standard deviation? We call it the standard deviation of the sample means. Now, when you take this one and put it in other words, if you took all the values there in the second last column, 4.9, 4.8, 4.6. Now, even if I only took a couple of them, okay. Now, if I go, mode 2, 1. Now, and if I go 4.8 equals 4.7 equals 5.6. If I just take 3 of them, look, equals. Now, and I go AC and shift 1, 4, and I go 4 again, look, and equal to. Look at how small the standard deviation is. You see, so if I put in all 20 of them that you have there, you'll actually get a very small standard deviation. And we're just going to focus on that now for a minute before the break. Okay? Now, it is much smaller, much narrower. No, we won't bother with that. Number 12 is only talking about the shape of the histogram you drew. That's what if you drew it, you'd get. The distribution has one mode. If we took more samples, we'd see is roughly symmetric. The sample means are centered around the center of the population distribution, and it's much narrower than the spread of the population distribution. And all of this we can get back from page 5. If you look at all the sample means there you got, none of them were very far away from 5.1. Yeah? Look at the standard deviation of each sample. None of them were very far away from 2.6. So in fact, our sample was a very good estimate for the population. Now, you described your chance of being one. You said it's possible, but it's not very likely. That's what you said, so your prediction was good. And the mean of this will be close to the mean of the population. Some will be closer than others. That's. Now, we'll just look at these here, and we've about 5 minutes. So we look at, I have 3 things coming up. So there's your population distribution. I'm going to bring in here samples of size 16 and here 64. Right, you might say 16 is small, but look, I want to get nice numbers because I can get the square root of 16 and the square root of 64, you know, so I can deal with nice numbers. So just look at how. Now, what I'm doing here, look, is I've taken now, look, 5 samples of size 16 and plotted them, and got their mean and plotted it, and I've taken 5 samples of size 64 and got the mean and plotted it. Now, let's build it up, look, to 100 first. 100 samples. Now, look at the shape the distribution is taken. It is roughly symmetrical, isn't it? You know, one mode. This one is certainly showing it, look. Now, let's go up, look, to 200 samples. Still holding out, roughly symmetrical, look. This one is roughly symmetrical. It's beginning to take this bell shape, isn't it? It's beginning to look like it's normal. Now, and this is a sampling distribution, look. There's 360, there's 400 of them, look. Look, it's bell-shaped, approximately normal. And this fella is bell-shaped, approximately normal. So we're getting here the sampling distribution of the sample means is a normal curve as well, a normal distribution. And of course, being normal means we can kick in with our 2 standard deviation, or 95%, our empirical rule. Okay, and the other thing about it is that it's the exact same thing that happened with the proportions in the morning earlier. We're getting this. Okay, now let's look at the means now, look. So just concentrate on the mean. These values come in here, look. Here, that's 5.1, and we'll be comparing these to 5.1, look. So when I take all these samples, look, and work them out, I get 100 of them. I get 5.15 and 5.1. So there's really no big difference between the sample size of 64 and 16. Sample size has no effect whatsoever on the mean. Now we're going up, look, to 200. Let's fast forward to 3. Look, they're hanging around the same, look, to 4. So 5.16. So I took 400 samples of size 16 and got their mean. You know, I got the mean, and then got the mean of all of those, and I ended up to getting 5.16. I took 400 samples of size 64, got the mean of each individual one, and then got the mean of all of those, and I got 5.12. Didn't make an awful difference that I had a much bigger sample size. Sure, it didn't. So the sample size has no effect on the estimate for the mean. Okay. Now, but look at the standard deviation now, and I want you to watch the bottom lines, look. Straight away, and compare it to 2.6, look. Straight away we see, look, if I go up to 100, it's much narrower. And look, if I look at this one, 0.65, if I multiply that by 4, I'd get roughly this. And of course 4 is the square root of 16. If I multiply this by 8, I'd get roughly this, and that's the square root of 64. So the thing is getting narrower, and we can see from looking at the distributions, look. So the sample size has a big effect here. And if I fast forward up along, look, to say even 200 of them, the same thing is keeping hold, look. And if I go up to 300, and finally up to 400, I'd say this time 4 times 0.63 is roughly 2.6, and 8 times 0.34 is roughly 2.6. Now, so the standard deviation of this distribution, or this one, which is the sampling distribution, is much narrower than the sampling deviation of the population. And in fact, it turns out to be, if the population is sigma, it's sigma divided by root n. Okay, by the square root of the sample size. Okay, so when you look at each individual standard deviation there, when you look at each of those, they're not too far away, look, from, and that's our summary page. So our population had one mode, mound-shaped and roughly symmetrical. The centre was at mu and the spread was there. When we took one sample, we had x bar, which was a very good approximation for this fella. Like every sample isn't too far away from 0.1. S, that look, the line there, the standard deviations of the samples are actually a very good estimate for this fella. Now, so that's our sample, that's our population. This is our sampling distribution of all the sample means. It'll be normal if I had every one of them. The mean of all possible sample means would have to be the true mean, wouldn't it? And the standard deviation would be the sigma over root n, and that is known as the standard error of the mean. And that's what that's called, the standard error of the mean. Okay? The standard error there, sigma over root n. Now, that's your central limit theorem down here. And when we come back, we might do maybe 10 minutes on reversing the question. Is that okay? I think, lads, we'll take the break, so thanks very much. Is that okay for us?